AI, or artificial intelligence, has been around since the 1950s and has gone through several booms and busts in the subsequent decades. Who knows if there'll be a bust in the next 10 years. But the term AI has taken a lot of different meanings within each of these time periods. But largely, the term has come to capture the science of making machines mimic the cognitive functions that we associate with human minds, such as perceiving, reasoning, interacting with one's environment. And there have been a vast amount of efforts towards the creation of intelligent programs and machines, but today we apply this label to two subsets of artificial intelligence that have produced most of the stunning applications that you're familiar with. And these involve machine learning and deep learning. And they're largely constructed by using algorithms to detect patterns and learn how to make predictions on large sets of data. And mainly what that means is that instead of having to identify all of the rules that make up speech, vision, or natural language and encode them into a representation that a computer can handle, the algorithms that we can think about in AI can be created by constructing a large set of examples that the algorithm then learns how to create. And this format has completely changed our expectations of what is possible with our computers. And here are some of the examples of that AI has tackled and made significant advances in the last decade. So we have image classification, where you generate a label of what exists in the image. Speech recognition, where you can produce transcripts of what is spoken. Translation, where you take sentences in one language and convert them to another. And then even more nuanced tasks, where you can take an image and produce a description of what is occurring in that image. And while solving each of those problems is interesting in isolation and have already produced products that are available to you today, when you combine each of these things together, you can start to create some truly breathtaking technology. And you can start to see why AI has been lauded as one of the most disruptive technologies of the last several decades. And there's no doubt that it's going to play a large role in the decades to come. So an example I'm showing here is a perspective of how an autonomous vehicle from Waymo, which is a subsidiary of Google, perceives the world around it in order to navigate dense urban environments such as the one shown here. And the advances within this industry has spurred investment of over $330 billion into over 2,000 mobility companies. And if we zoom out, it's hard to find an industry where AI is not delivering impact in one way or another. The applications here include things such as market forecasting, user sentiment analysis of customer reviews, recommender systems that we know and love and interact with in applications such as Spotify and Netflix, the facial recognition software that you interact with every day to unlock your phone, and even the fraud alerts you get when you purchase something on a credit card that's outside of your normal behavior. Now, in the last couple of years, and largely why AI has developed so much excitement in the past year or so, is that we've also been able to reverse a lot of the problems that I mentioned previously. So now we can take things as input in textual format and have AI models generate more complex outputs. For example, here, simply providing the textual prompt leopard can lead to hundreds of images of leopards that are realistic, good-looking, and quite plausible. Or even more explicitly, we can now use description of images to produce the artworks that you desire. And in the last couple of months, with the rapid rise of OpenAI and several other generative AI companies, we've seen the development of conversational systems where you can interact with an AI system in a manner that is quite human-like and helpful for numerous tasks. So I thought I'd use it about 5 minutes before the meeting to create a couple examples to demonstrate what this technology can do. So in the top right, I asked DALL-E to generate an image that reflected what AI in the future of business would be like. And it seems to think that the future of business will largely look like the Matrix. I then asked ChatGPT to describe to me how it works, and it did a pretty good job of doing that too. And while these examples might be limited in nature compared to the things that you're working on in your applications, I think one of the most exciting things about this form of technology is that it now presents the ability to lower the barrier of entry for the development of really cool applications to just describing them in text. And while many things may be out of reach at the moment, this form of AI, can everyone hear me?
Yes.
And while many things may be out of reach at the moment, this form of AI is already helping programmers eliminate repetitive tasks, is helping writers ideate as they write articles and papers, and I could go on about many other applications. And if you look at the pace of innovation within this space, it's simply staggering. The number of startups within this space is huge. And at the same time, we've also seen established players within this space start to reinvent themselves as AI-first companies, whether that be in the education, finance, infrastructure, automotive, healthcare, or even gaming sectors. And there's a real belief that we can reimagine how we organize our cities, move around, learn, and so much more. And the belief that we can reimagine how we do things is central to how we are doing things at Google. Our CEO, Sundar Pichai, has regularly said that AI is causing us at Google to rethink everything we're doing in our aim of organizing the world's information and make it universally accessible and useful. So let me take a step back for a moment and talk about what it is you need to be successful with machine learning. The first is high-quality data sets. And since a lot of machine learning learns by example, it's pretty self-evident that you need good examples. I used to say that you need large quantities of data, but I think it's important to stress that although machine learning does work best when you have a lot of examples, the quality of those examples is equally important. So if you think about an example of learning your own native language, or even learning the concept of a dog. Imagine you grew up never seeing a dog. You never read a book with a dog, your family never said the word dog, you never even saw one on TV. Now you go outside and suddenly you see a dog for the first time. What do you think are the chances you spontaneously say that's a dog? It's pretty slim. But there's actually a much deeper topic, and I could talk about the importance of picking your training data, setting aside data to test with, but for now I'll leave you at this. You need to train your ML systems with data that is representative of what you will encounter in the real world. ML systems are the ultimate example of garbage in, garbage out. Secondly, you need a whole lot of compute. Your brain is an amazingly compact and powerful example of an electrical chemical computer. The average human brain weighs about 3 pounds and consumes about something like 20 watts of power. To replicate that, we need systems that are much bigger and much more powerful since computers are much less efficient. In fact, it's more compute power than most companies have available in their data centers. And realistically, the cloud is the only way that companies can tap into this kind of computing power. And lastly, you need good tools and frameworks. And I could describe 100 different ML models to you in a few minutes, but they're quite tricky to implement. So you really can't afford to try and implement them starting from scratch. And if we're successful in meeting those 3 criteria, then we can start to really create some really intelligent models that can handle the kinds of things that we want to do. So for example, if you never knew what a dog did, and I showed you a couple of examples, you'd be pretty good at it after a few minutes. And now, while these principles have led to many amazing applications that I previously mentioned, they also pose unique challenges. The first being that as AI and machine learning applications have become more powerful, they have also become increasingly more complex. More specifically, if we look at one of the most popular forms of machine learning that consists of deep neural networks, the size of these models has generally doubled in size every 3 months. And for more state-of-the-art models, the number of parameters that define these models are on the order of billions and will quickly approach trillions. And we haven't exactly seen diminishing returns on scaling our models, which is kind of a scary concept. But at the same time, we also need to ensure that the increase in our model complexity is also proportional to the amount of data that we use to train it, which has also led to an explosion in the amount of compute needed to develop these models. So the result of these 2 trends is that the compute cost of developing AI applications is now staggering. Depending on who you ask, over the last decade, we've seen the computing demands of these models increase over 750 times every 2 years. Whereas the innovation in our hardware has only sustained a growth of over 2x every 2 years, which has led to some really unique innovations within this space. And one of the key ways that we're addressing the increase in computational demands associated with AI is through the design of specialized hardware that are often referred to as AI accelerator hardware. What that means is it's a specialized device designed for ML applications. And the terms that you're likely familiar with are graphics processing units, or GPUs, or tensor processing units that are unique to Google. However, the essential nature is they're optimized to perform the calculations that make up the majority of these models, which, when you really boil it down, is matrix multiplications. And these specialized compute can perform these computations up to 1,000 times faster than regular CPUs. And when you take these individual chips, you can start to design supercomputer systems that allow you to scale your compute performance, enough to meet these challenges. But realizing these benefits requires that you understand the joint interaction of compute, memory, network, power, and other requirements of this infrastructure. But at the end of the day, what this allows us to do is take tasks that typically require months to complete and shorten the time needed to develop them to hours or even minutes. But also, on the flip side, we can take our same models and scale them by 10 or 100x to see what kinds of things are possible. And within this arena, we are simply getting started. Google's been designing custom accelerators for just over 10 years now, but the need for these kinds of designs has never been greater. Not only to meet Google's needs, but also to meet the needs of our customers, who seek to leverage these technologies to power their businesses. And if we look just at the growth in generative AI in the last 2 years, we saw more than twice the number of generative AI projects in 2023 than in all of 2022. And we know this is just the tip of the iceberg. So if you're interested in things at the intersection of AI and computer architecture, there's going to be a lot of demand for you. Now, to step back, while a lot of this progress is extremely exciting, it's equally important to remind ourselves that this technology is not infallible. In fact, one of the fundamental aspects of AI is that its advantages often come at the cost of fragility. And what I mean by fragility here is that AI components can fail in unexpected ways. And this is simply not a problem of faulty training data, but one of the limitations of the models themselves. So in a famous study by Christian Sesgeti and his colleagues, the authors demonstrated that by carefully applying small modifications to input images that you provided the AI models, you could cause a successfully trained machine learning component to produce an incorrect classification. And these inputs are known as adversarial examples, and the discovery has caused concern over the safety, reliability, and security of AI applications. But beyond adversarial examples, the number of edge cases that AI must be able to handle is quite large in practice. And despite our best efforts to estimate all the foreseeable scenarios that these systems must be able to deal with, we often have no way of understanding if we've identified all the possible threats to or the failure modes of the system. And given the fragility of the systems, one of the fundamental things that we have to understand is how to develop principled ways of identifying when these systems are tasked with handling situations that they weren't prepared for. And getting this right is extremely important. And while there's been a lot of work within this space in recent years, there's still a mountain to climb with a steady drumbeat of news stories of AI failures that range from the trivial to the tragic. And building confidence in these systems will require holistic analyses of their design and interactions with the world, to ensure that the technology that we develop will be consistent with society's goals. Now, a lot of that work is outside of the scope of typical classical AI. But since I spent the majority of grad school working on these problems, I'll briefly flash some of these efforts. One of the realms that AI has seen a tremendous amount of activity is the application of formal methods to these applications. And formal methods here refers to a class of mathematical techniques used to specify what a system can or cannot do. The central idea here is either A, you construct a proof that your system is correct, or B, you identify a counterexample of an incorrect behavior. And using these models, you can perform analyses of machine learning components. Classically, the majority of this work has occurred within the safety critical space, where a machine learning component is deployed in an automotive system or a drone, where the stakes are a little bit higher for incorrect behavior. But classically, you can also apply these to simple AI applications as well. So, before I open up to questions, I'd like to stop there and thank you for being here. But I'd like to summarize a few fundamental questions. AI has fundamentally altered our expectations of what is possible with computing. And it will change many industries in ways that are hard to predict, and there are many challenges to overcome. But I think it's a great time to be optimistic with respect to what we can achieve in AI. And with that, I'd like to open the floor to questions.
How close would you say Google is to HEI?
On the record, off the record. AGI is an interesting concept. I think the industry in general is probably, I don't like to make predictions, but at least a decade away from AGI. A lot of the things that we are seeing in the common press today are fancy applications of transformers that have existed for the last 5 years. I think there's a difference between the perception of intelligence and actual intelligence. Many of the failure modes of a lot of this technology show you that they don't understand the underlying task that is being trying to be learned. So I think from that perspective, we're quite, in mimicking intelligence, we're very close. In actually achieving intelligence, probably not close.
What is AGI for folks that
So so AGI is artificial general intelligence. So artificial intelligence is where we can start to create representations of intelligence, which is a lot of the stuff that I've been talking about for the last 15 minutes. AGI is the next step in intelligence where the underlying system itself is able to sense, perceive, and actually reason for itself, which is an order of magnitude more difficult than a lot of the stuff that we're working on.
I know there's a lot of overlap between data science and machine learning, and I was just wondering how you would define the differences between the two.
That's a very good question. I think, okay, so the differences between data science and machine learning. So a data scientist, at a very broad level, is tasked with solving some problem with data. That's it, right? And they have a lot of tools in their tool belt. Some of it is statistical learning, some of it is regressions, and all these different types of tools. Machine learning is just one of them. At the end of the day, machine learning is you have a set of data and you have a set of tasks that you want to accomplish. And machine learning is the way to get there. So from a perspective, a data science leverages machine learning to solve the problems.
Which company would you say has the best LLM? Is the farthest in AI?
No bias.
Google, of course. I think it depends. What do you mean by the best LLM? So one of the things within this space, especially machine learning in general, is the performance of an underlying model really depends on the benchmarks that you use to evaluate. So within the large language model space, there's a suite of benchmarks that they're evaluating. Now, one can argue that different benchmarks have more relevance to the power of an LLM. The second thing is whether those benchmarks are truly representative of what we want these LLMs to actually do. So from a benchmark perspective, Gemini has just been shown to be the best. GPT-5 could come out in the next couple of weeks and actually destroy those benchmarks. So I think at the same time, I think the more relevant question is, what is the best LLM at the current time? Particularly within this space where everything moves within 2 weeks. If you'd asked me that question in December, I would have easily said GPT-4. But now, with the release of Gemini, I haven't played with Gemini too much, but they said it's better. Facebook just released Llama 3 weeks ago. I haven't played with it, but maybe it's the best. So I'll leave that question to you.
What about like large language models trained on like smaller data like Microsoft Phi 2? What do you think about what do you think about like large language models that are trained on like smaller chunks of high quality data like Phi 2? And like I think that was by Microsoft. So do you have any opinions on like small data for like large language models?
Yeah, I don't think I have particular opinions. I think it's one of the things that fundamentally businesses are going to have to do. I think within the space of AI, there's about 7 companies that regularly train large models. It's Microsoft, NVIDIA, Google, Facebook, and a couple other companies. Now, a lot of companies outside of that don't have the infrastructure to be able to train a foundational model themselves, but they do have very custom data that is unique to their business. So this is going to come out of necessity. And a lot of this has been increasingly successful. So one of the good things about machine learning is if you take a previously trained foundation model and customize it on a small data set, it can really do some amazing things. And I think as more people start to take these models and customize them to their applications and then feed those results back into the people who develop the foundation models, we're only going to see more and more incredible technology.
Where do you see the interaction of smaller on-device computation versus the cloud-based AI computation?
Just repeat
Yeah. So where do you see the interaction of like on-device computation of AI, say language models versus like cloud-based? And, like, where do you see more of the future trending towards, or the intersection?
Yeah, I think that's a good question. I think there'll be two parallel streams. In terms of a lot of the companies that are developing this technology is to create things that everyday consumers can interact with on a daily basis. And those things are going to have to run on your devices. If you think about how revolutionary the smartphone was with respect to all of our experiences. And if you really want to tap into the potential that generative AI has, we're going to need to bring it down to that level. Now, the types of capabilities that these smaller models have with respect to the larger models is the smaller models are simply less capable than the larger models. So if you want to interact with more complex systems, that's going to have to happen in the cloud. So previously in machine learning, it used to be the case where we could take a single model, deploy it on a GPU, and run that inference for thousands of users. We've now reached a stage where one of these models doesn't fit on a single chip, but requires clusters of chips to run. So there's a particular limitation there. Now, there's a lot of advances trying to figure out how to take that model and run it on your device, but there's a lot of work that still needs to be done. So in my opinion, I think the most fundamental technology will be in your hand, but there will be a certain class of things that cannot be run on your device.
So, do you think AI should be regulated, and if so, how?
Yes. Do I think AI should be regulated? Absolutely. I think one of the fundamental things about AI is that the things that scare me the most about AI are already possible. It's not, I don't need AGI to have an impact on society. Whether that results in biased applications, whether that is a fundamental assumption that AI is more powerful than it is. I think one of the dangers with AI is, as a society, we are very trusting of predictions that come from sophisticated mathematics. Whether that sophisticated mathematics even makes sense in the first place. If I slap enough formulas and proofs on the slides, for some reason you'll believe me. But they're fundamental applications that AI should never be. One of those is social applications. You cannot tell me that you can train a sophisticated enough model to predict the outcome of a human being. So in that space, I don't think it should be used. That's my opinion. Now we have to figure out what lawmakers and other society believe that can happen. So yes, should it be regulated? Yes. Who should be in the rooms of those conversations? Essentially everyone. From a practical standpoint, how we're going to do that, I genuinely have no idea. One of the things is we've been talking about data privacy within the United States, or even at the globe in general, for the last 10 years. And the outcome of those conversations, while some of them have been increasingly effective, is now I have to click cookies every 5 minutes on my device. Now, does that actually make an impact on privacy? I don't know. So it's going to take some really creative folks to figure out how to, once those regulations are actually defined, how to enforce them.
So speaking of security, I'm sure there's a lot of health companies out there that are trying to implement AI models as well. How are they planning on remaining HIPAA compliant while training the models on medical information per se?
So, this is one of the things that's outside of my realm of expertise, but currently these applications exist. One of them is through data anonymization, which is one way that they train these models. It's really complicated. There's a few companies in pilot. It's not generally accessible. I think we're still really evaluating how to do that. There's probably gonna be some missteps on the way there, but I know it is happening. So yeah, I would agree. I'm not the person to ask about that.
Thank you, I appreciate it.
So my question was about like, just like in like kind of like the realm of like jobs and like a lot of people talk about like AI is gonna take jobs. Are there any like do you think that's true, and do you think that there are any like fields that are gonna like almost be like wiped out because AI can just do their job, or are there any fields that you think are completely like kind of like future proof from that?
Yeah, that's a really good question. I think my perspective on this is there will be two things that happen in there. One, there will be an entire class of jobs that disappear. There will be also an entire class of jobs that also appear with respect to AI as well. I think the more repetitive a job is, the more likely it is to be eliminated. For example, data entry. We now have generative AI has shown incredible capabilities of scraping information on the internet. Is it really good? No. So that's an example of a job that just got created. Maybe you don't spend your days entering data into spreadsheets, but you spend your days evaluating whether it was correct. And once that gets good enough, there will be a fundamental limitation there. What will your new role be within that space? Within computer science, the closer you are to the metal or the hardware itself, the safer you are. But then again, that's not necessarily true, because we also have AI trying to generate future chips for us. In fact, even at Google, I saw a project just a couple weeks ago figuring out how to explore chip architectures through AI, or what parts of the workload you should optimize. I really don't think AI is going to take our jobs. They've been saying AI is going to replace radiologists for the last 50 years. They're still around. So I wouldn't worry about that too much.
Yeah, I had one question. So you mentioned near the end that in your graduate school you did research on application of formal methods. Yeah, so like currently I'm taking a theory of computation class, kind of learning about NP, P, code, NP, and all these classes. How has that helped you in your career, or if it has?
Grad school in general, or the formal methods?
Let's say both.
Okay. Yeah, I think I'll answer it in the second sense first. Formal methods within machine learning. I think classically in computer science classes, you take a lot of classes that teach you how to program, they teach you how to think about ethics, they teach you about various classes within computer science. But one of the things that they don't really teach is principled ways of testing and evaluating software. And from that perspective, not just constructing unit test cases, but coming up with more powerful proofs over the semantics of the program. So instead of saying, how do I test my program? You reverse the question to ask another question, which is, how would I construct a completely bug-free program? Now that was the perspective of formal methods. When that was applied to AI and machine learning, it came to be, if I have a system that is entirely a black box, how do I prove that a black box operates correctly? Which, in a sense, is kind of a trick question. If I was able to kind of figure out all the possible ways that my system could operate, I wouldn't need machine learning. That's the whole reason we use machine learning. One of the great things that people say about machine learning is we typically use machine learning when we don't have any better ideas. We showing a bunch of examples, optimize the model, and out come some predictions. But if we were asked to explain how those predictions come through, we typically don't have a great understanding. So more formal methods ask me to figure out how to come up with more rigorous proofs of these systems. Now, with that perspective, it started to influence the types of problems that I thought were relevant for AI to solve. So in my career now, I'm pretty typically skeptical of claims that AI has solved a problem or AGI is here. The first part of that process was going to grad school in the first place. I think there's a lot of exciting things within this space, and grad school allows you to explore those things for a time, for a significant chunk of your career. There's a lot of topics that maybe you want to go deep with, or maybe you're not exposed to. It allows you to work on problems that are not relevant just for today, but may be relevant in 10 years. So I think from that perspective, I think it's given me a broader perspective of types of problems.
Any other questions?
What are your thoughts on leveraging quantum computers for training generative AI models? Is it being already done? Is it possible? Yeah, so I was asking, what are your thoughts on leveraging quantum computers for training generative AI models? Like, is it already being done, or is it possible?
I'm not familiar entirely with work of using quantum computers to train generative AI. I know there's a lot of challenges within the quantum AI space. But I think, from this perspective, I don't think that it would be the right solution. So, for example, training a particular foundation model costs $1 million. Now, if I take a quantum computer that also costs $1 million to develop, only to train my generative AI compute, then I've actually made the problem less tractable. In the sense, most of the questions that we're trying to answer Google is how to make trading cheaper so that customers can leverage it within our applications. And at the current moment, I don't see how quantum computing can make AI trading cheaper. It could make it faster, but faster at what cost? Any other good questions?
So talking about like application on the right now, like let's say I want to use a model lifetime on an iOS app and take advantage of the neural processing unit that Apple has. You would have to have a core ML model to take advantage of that. Do you think there will be a like generalized framework that everyone uses, or do you think it's just going to be like how it is right now, where each is going with their own thing?
That's a good question, and I think it's a strategy question from the company's perspective. There are efforts to standardize how machine learning operates on different platforms. So I'm not sure if folks are familiar with ONNX, but it's the Open Neural Network Exchange format that is actually being actively developed by AMD and a couple other companies, including Microsoft, Google, and several others. But the idea is you take one neural network, use this interchange format so that it can run on a platform agnostic device. That's great for us, but in terms of the companies themselves, if you have the devices, the ecosystem, the models themselves, and you can vertically integrate that in your own company, then there's not too great of an incentive to do that on another application. So it's kind of the company's strategic advantage. If it was to be the case that we had an exchange format, then a lot of the customized hardware that I talked about in this presentation would become a commodity. Just think about how cheap memory is in one computer system. So I would love for that to happen for us, but from a company perspective, they're probably not going to invest very hard.
Thank you for that answer. I appreciate it.
So coming from the hardware perspective, and I have a limited background in it, but just out of curiosity, So we've kind of come from GPUs to tensor processing units, and we see companies like Meta and Microsoft coming up with their own specialized AI chips. What do you see as future developments in the hardware space?
So yeah, that's a great question. In the hardware space, I think we're going to increasingly see more custom style chips. NVIDIA was the first one to be able to realize that they could convert a graphics processing unit to run AI applications at scale increasingly fast. Google, at the time in 2010, decided that basically the story of how Google developed their chip was they asked the question of if every user in the world talked into their device for 3 minutes, and I wanted to convert that text to speech based on their AI models, it would require them to triple their data center footprint. Now, that wasn't realistic. So the solution to that problem was to develop the TPU chip so that they could do this at scale. Now we've reached a point in today's application of Gen AI models where this is again the case. For example, if a company says, I want to take GPT-4, multiply it by 10, how would I train that model? If they looked at their compute infrastructure, they would realize they didn't have the compute, which required them to fundamentally change their infrastructure as well to be able to do those kinds of applications. So it's not going to be, in this sense, it's not a wish of these companies to develop custom accelerators, it's a requirement.
Thank you.
Any other questions?
Hi, so when you got into Google, you probably had some like goals or some like kind of like mindset like going in about like AI or like what you wanted to do with the company. How did that kind of align with what Google, I guess like had set for you and like what problems you worked on?
That's a good question. So when I was leaving grad school, a lot of the work that I had been doing was applying AI to autonomous systems. And I had been interested in figuring out how to see how these systems were applied at scale. I didn't really have like a concrete idea of what that entailed because I didn't know what it was like to train a chip on thousands of chips, but that's what I wanted to do. So at the time, a role opened up within AI infrastructure, which wasn't exactly related to training models on thousands of chips, but rather characterizing their performance. So that was a natural fit for me. But backing up to Google in general, AI is fundamental to everything, practically every product we have. Whether that's within Google Meet or Gmail or whatever product area within Google. So there's a ton of projects that you can choose from. So I think at a company at this scale, it's really about your interest. If you have a particular interest within the AI space, there's probably a problem within Google that you can work on. It's one of the things that even if you're working on something that might improve the performance of something by 1%, at a company at our scale, 1% could be the difference between 30,000 users using the product or not. So there's a lot of opportunity.
Thank you.
Any final questions as we wrap up? Could be about AI in general or Google. Sweet.
What was kind of your first experience with AI and what got you into it?
That's a great question. My first experience with AI was a project called the F110 project, which I think is still available. But the idea here was how would you take a 110 scale RC car, which is a Traxxas rally car if you've ever heard of them. They're remote control cars, they go up to 40 miles an hour. But there's this global competition every year for colleges throughout the United States where you can program one of those to drive around the track autonomously. So at the time, I didn't know anything about microcontrollers, didn't know anything about AI, but I knew I wanted to get into atomic science. So my first adventure into AI was figuring out how to train one of those models to navigate down the racetrack. So it was training one convolutional neural network to detect images within the track python, which ended up being a really exciting project. And from there, the interest grew. But I think that project, the F110 project, is alive and kicking. If anyone wants to do it, it's a lot of fun. You get to travel across the world to conferences to race remote control cars. And if you're in grad school, it certainly characterizes research. Shameless plug for F110. Questions? That's good. With that, thank you all for coming, and I appreciate you being here.